In the last theorem, we actually proved that if you take eigenvectors of different eigenvalues, they actually form a linearly independent set. And we also said that if you take a basis for each eigenspace and you put them together, you get a linearly independent set. So we want to use this in an example. So if possible, find a basis for Rn containing only eigenvectors of this matrix here. So in example, let's see, this is the example we have, example 3.1.5. We found the eigenvalues. We have lambda 1, which was -1, and lambda 2, which was 2 for A, and we found, actually, and lambda 2 equals 2. And we also actually found a basis for each of them. So the basis we got a basis for E minus 1 and E2. So the basis for E minus 1 was -2, 1, 1. And the basis for E2, that one had two vectors. And so we got 0, 1, 0 and -1, 0, 1. All right, so what we now know is if we take this set and this set together, it's going to be linearly independent. So from the proposition 3.1.4, from proposition 3.1.4, if I take -2, 1, 1, 0, 1, 0, -1, 0, 1, this is linearly independent. So you cannot use vectors of different eigenvalues to build an eigenvector. And so this is linearly independent in R3, and R3 has dimension 3, and I already have 3 elements. So since the number of elements in S is 3, which is the dimension of R3, S is a basis. Made of eigenvectors. All right, so in general, B1 through BK, if you take all of these bases and you put them together, that's going to be a basis. Well, for the sum of the eigenspaces of A, this subspace might or might not be all of Rn. So we'll talk about this further in section 3.3.3. It will be important there to know when you get a basis for eigenvectors and when you don't. At this point, it's not clear why that's super interesting yet. So let's save it until we know it's interesting, and then we'll come back to it. So section 3.3.3, that's when we'll make this a bit more specific.